In this lesson, I'm going to talk to you about polar curves and calculus as it relates to AP Calculus BC. This is topic 9.7 in the official AP Calculus curriculum. And if you want to print the guided notes sheet that I give my students, you can go to this bit.ly link and print there. So let's start talking about calculus with polar curves. And we're going to do just a little bit of a review of things that you should have learned in either Algebra 2 or Pre-Cal. Polar curves are graphed by coordinates that are in the form r theta. Theta is an angle measured counterclockwise from the positive x-axis, and r is the distance from the origin, but in polar curves we call the origin the pole, so technically it's the pole, but if you want to call it the origin, that's fine. And we will often need to convert polar to rectangular coordinates, so we want to go from an r theta to an xy, and I'm going to very quickly show you where these formulas come from because they are two fairly easy to remember formulas, but it's also easy to mix them up. So I'm going to show you just for a second how we can figure this out if you happen to be forgetful. And so we have a point r theta. Theta is the angle measured to the positive x-axis. So we come up off the x-axis a certain angle, and that angle is theta. R is the distance or the length of that segment that connects the points to the origin. And if we want the x and the y coordinates, we can create a triangle. The x coordinate is however far we travel to the right, and the y coordinate is however far we travel up. And if I want those coordinates, we can channel our inner trig brain, thinking SOHCAHTOA, and if you think of sine, the sine of theta would be opposite y over the hypotenuse, which is r, and the cosine of theta would be the adjacent x over the hypotenuse, which is r, and if you multiply both of those by r, you get our formulas. X equals r sine theta, r cosine theta, and y equals r sine theta. And so there is the derivation of those formulas if you happen to forget them, and we will use that a good bit in AP Calculus BC. So let's talk about derivatives. So now we're going to get into the calculus. What does dr d theta tell us? And what dr d theta will tell you is how r is changing. Now that's a big earth-shattering statement there. Derivatives do tell you how things change, but more specifically, r is the distance from the origin or the pole. And so if dr d theta is positive, if any derivative is positive, that means that thing is increasing, and in this case that thing is r. So r is increasing, and if r is the distance from the origin and that is increasing, then your curve is moving away from the pole or the origin. And similarly, if dr d theta is negative, that means r is decreasing, and if the distance to the origin or pole is decreasing, then you're moving towards the pole. So there is what dr d theta would tell you. And then if you want to find the equation of a tangent line, we still will need, and this is true every single time, every time you write the equation of a tangent line, you need a point and a slope. And when we do tangent lines, we want our points to be in rectangular form. We want an xy point, and the slope is almost always, there are some exceptions, but almost always by evaluating the derivative at typically some x coordinate. But the problem here is we aren't given x's and y's, we are giving polar curves, and I kind of jumped the gun on there. But slope is always a delta y over delta x, which in calculus is dy dx. I'm going to reposition this dy dx. Rewrite that down here. Dy dx, derivative of y with respect to x. So if I need xy and I need a dy dx, we're going to have to use that x equals r cosine theta, y equals r sine theta, which will convert your polar curve to a parametric curve. And so they're not t's, but we do have x and y both defined by a third independent variable of theta. That is a parametric relation. And then once you convert it to parametric, you can just use your, you can just use what you know about parametric curves to find the slope of the polar curve. So we're going to do one example of that, and that is really all I'm going to do in this one. I don't have a whole lot of examples, just this one example for differential calculus, and then in a separate video I'm going to do the area of a polar curve. And so let's look at this one. I want the equation of a line tangent, and I'm immediately thinking, as soon as I see equation of a line tangent, I immediately think I need a point and slope. Every single time I have written an equation of a line, my entire life, point and line, I've always needed a point and a slope. I don't think you will ever have an exception to that. The thing is, we're looking at a polar curve, and if I want a point, an xy coordinate that is on a polar curve, I need to convert my polar curve to rectangular. And so I'm going to go y is r sine theta. The r is that expression, so I'll just go ahead and take the r out. Y is r, which is 2 sine theta, times sine theta, which if you want, and it's going to be a little bit more convenient down the road, you can write that as 2 sine squared theta. And x is going to be r, which is 2 sine theta, times the cosine of theta. And with that, I can now find my y coordinate when theta is pi over 6. So that will be 2 times the sine of pi over 6, and then I want to square that. And similarly, I can find my x coordinate at pi over 6, which is going to be 2 sine of pi over 6 times the cosine of pi over 6. And I'm going to clean those up in just a second. And there we go. I told you it would be a second, and it was. Here come bells. Okay, bell's over. And it is sheer coincidence, I just noticed this, that the final ordered pair for my polar curve happens to be the same as the coordinates on the unit circle at pi over 6. That is coincidence. Please don't think that that's always going to be the case. You do need to actually go through your x equals r cosine theta and y equals r sine theta. So now we have the point. The slope, unfortunately, is the tricky part, because if I want to get the slope, I need dy dx. And in parametric relations, to get dy dx, we need to do the derivative of your y expression, and in this case it's with respect to theta, over the derivative of the x expression with respect to theta. And they're not painful derivatives, but we do have, for dy, we have a chain rule, because that is I'll rewrite this, that is 2 times the sine of theta squared. So we'd have to chain rule that. And the derivative of x is going to be a product rule. It's 2 sine theta cosine theta. We have to product rule that. So I'm going to have a big ugly fraction. Give myself plenty of room here. And the derivative of my y expression, I'll bring my 2 down. That will be 4. I will leave the sine theta alone. To the first. Then times the derivative of sine, which is cosine theta. And that's it for the numerator. That one wasn't too bad. The denominator is a product rule, and I'm going to ignore the 2. I'm going to leave the 2 out, and I'm just going to product rule the sine and the cosine. And so let me get rid of that green. That's confusing me. So I'll have 2 times, and now my product rule, the derivative of sine theta is cosine theta times cosine theta, plus, now I will leave the sine theta alone, times the derivative of cosine theta, which is negative sine theta. Then I need to plug in pi over 6 to that. So now I need to evaluate my dy dx at theta equals pi over 6, which is going to be this thing, 4 times the sine of pi over 6, cosine of pi over 6, all over. And as I rewrite this denominator, I'm going to clean it up a little bit. That cosine, that's cosine squared of pi over 6 minus sine squared of pi over 6. Close parentheses. And then we will evaluate that. And I already have the coordinates up here. So sine of pi over 6 is 1/2. Cosine of pi over 6 is root 3 over 2. My denominator, cosine of pi over 6 is root 3 over 2, and we will square that, minus the sine of pi over 6 is 1/2, and we will square that. And this cleans up, if I'm not mistaken, to just root 3, so 4 and the 2 times 2 will divide out, so we have root 3. And in the denominator, that's 3/4 minus 1/4. That's 1/2 times 2 is 1. So the slope does end up being a nice clean √3. And here's where you may be tempted to quit because we've done a whole lot of writing for this one problem. But remember, we need to write the equation of the tangent line. So let's drive this one home. Therefore, my tangent line is, and I'm a fan of point slope form, so it's going to be y minus my y coordinate of 1/2 equals my slope of √3 times x minus my x coordinate of √3 over 2. And remember, we are using the point that we got way up here and this slope to create that tangent line. And we are done. So that is all I wanted to do with the derivative differential calculus. And if you want to see a video on how to do areas of polar curves, that's going to be my next video, which I'm going to record as soon as I'm done with this one.